So we've learned all kinds of stuff about gas laws, but can we use that now to do some stoichiometry? Well, yes, we can, of course. Here's an example. So let's say you've got 1.22 liters of methane gas at 15 degrees Celsius and a pressure of 328 kilopascals. Let's say you want to do complete combustion of that methane gas. Let's figure out how much oxygen, and we'll figure it out as a mass, that you need for this reaction. So to start with, in any stoichiometry problem, you're going to write your balanced chemical equation. In this case, we're writing a combustion equation. This is a great review of Unit 2 as we're preparing for our exam. So we've got methane, CH4, plus oxygen. So in any combustion reaction, your other reactant is oxygen. And that will make the two products carbon dioxide and water. Then we just need to balance that. So you can see how I've balanced it here. There's one carbon on each side, so the carbons are already good. Next, I do the oxygens. Next I do the hydrogens. There's 4 hydrogens on the left side, so I need a 2 in front of the water here to make 4 hydrogens. Then I just count up all the oxygens I've got on the product side. 1, 2, 3, 4, right? 2 plus 2 is 4. So I put a 2 in front of the O2, gives me 4 oxygens, and it's all balanced. The next move I need to do is get into mole land. If you remember, this was true of every kind of stoichiometry problem we did. If we started with mass, before you can do stoichiometry, you got to get into moles. If we started with concentrations, before we can do any stoichiometry, we've got to get into moles. So let's use our equation PV equals nRT to get into mole land. So write out our given. We know the pressure, we know the volume, we know the temperature. Watch out, the temperature is in Celsius. This happens like every time. You'll get temperatures in Celsius and you can't do anything with temperatures in Celsius. It's got to be in Kelvin. Really common mistake is to forget to convert. To convert temperature to Kelvin, you want to add 273.15. Now it's in Kelvin and you're good to go. We also always know R, right? So R is a constant 8.314. And then we're going to be solving for our moles. So here's our equation, PV equals nRT. We need to rearrange this for N. So I can divide both sides by RT, cancels out my R, cancels out my T, and I've got a nice equation for N. We're going to be plugging in all those numbers. I can just show you what that looks like all plugged in so you can see those steps. So moles is equal to the pressure. The pressure is the 328 kilopascals multiplied by the volume, which is the 1.22 liters, and all divided by RT. R is that constant, 8.314. And T is my temperature in Kelvin, 288.15. There we go. So it's a bit slow. There you go. So the moles that you get of your methane gas is 0.167 moles. Okay, so first step, write the balance equation. Next step, convert to moles from wherever you start. And in this case, it's from gas laws. Now that I'm in mole land, I can do stoichiometry. So if you remember how I set up stoichiometry, what I do is on the left side, I'm going to put the actual number of moles of stuff. X on the top here, this is the moles of the thing I want. So that's the moles of oxygen. That's what I've got on top here. On the bottom is the moles of the thing I know. That's the methane. So then on the top here, I'm going to put the coefficients in front of those same compounds. So oxygen's on the top on the left. I put the coefficient in the balanced equation on the top on the right. On the bottom, I put the coefficient in front of methane. There's nothing there, so that must be a 1. So I put a 1 on the bottom here. Pretty quick to rearrange this for x, we're just going to multiply both sides by the 0.167. I can show you that. So I'll just erase this. So we multiply both sides by the denominator here. You've done this lots. Multiply by 0.167, and that's going to kill out my denominator here. Kaboom! And we'll multiply this side as well by 0.167. So that's how I get that number right here, the moles of oxygen, which is 0.334 moles. Now I'm writing down these numbers rounded off, but I'm keeping all of these in my calculator, right? As I go through, I'm not going to actually round off until the very end. So these numbers, you're holding the whole number in your calculator. So we've got moles, right? But that's actually not what we're asked for. If you look back to the problem, you're asked for the mass of oxygen gas. So our last move is going to be to convert the moles of oxygen into a mass. And how do we do that? Well, we use mass is moles times molar mass. So let's give that a try. We'll plug in our moles here, which is 0.334. The molar mass of oxygen is 32, right? You can get that by just doing 2 times the molar mass of 1 oxygen, which is 16.00 grams per mole. That's how I got that 32 right there. Multiply that out and I get 10.7 grams. That's my mass of oxygen.